Okay, student, let us see what is there in this question. Outline by reference to nuclear binding energy why the mass of a nucleus is less than the sum of the masses of its constituent nucleons. Okay, so by the reference to nuclear binding energy, so we have to talk about the binding energy first of all. So point number one is like the students, those who do not understand what is this concept about the binding energy, and the students those who understand what is this, they can clearly know, they know it, that you have to just write it that when the nucleus is created, the energy is released. Okay, so let me first go into a bit of details. Will not be wasting a lot of time here, but a little of it. See, the nuclear binding energy is defined in two different manners. Number one, it is the energy that should be given to a nucleus. Like this is a nucleus, and yeah, like four nucleons are there. What is the energy that has to be given to it so that it breaks down into four constituent nucleons, and they will be separated up to, and they will go up to the infinite distances. So this is the binding energy. So I repeat, the energy required or energy given to a nucleus so that it breaks down into constituent nucleons and they go to infinite distance. Even that is the condition. Okay, now binding energy can be defined in another manner also. So these nucleons, they are now coming together and they're creating a nucleus now. So if they're coming together and creating a nucleus, they will be releasing some energy. So the energy released is called the binding energy. So this is released, and here the energy required, this is energy required, and this is energy released. Okay, this is energy required. So the energy given to the nucleus so that the nucleus breaks down into the constituent nucleons, even that is called binding energy. And when they come together, again some energy is released. Now it was Einstein who asked this question, that okay fine, there is a nuclear reaction taking place, or there is some reaction taking place, why the amount of energy released in these nuclear reactions is enormous. From where is that energy coming? Because by the principle of conservation of energy, energy cannot be created nor destroyed. So from where is this humongous amount of energy coming? A bit of energy is understandable, but this is like a lot of energy is coming out. So he created this formula, like E is equal to mc square. So according to him, the mass can be converted into energy. So this is like the binding energy, which is like delta m into c square. And he said that there is some mass which is lost during the process. Now in this first case, energy is required. It means you have to provide a lot of energy, and that energy will be given to it, and the this will be created. So the energy is converted into mass in this. But if you going the other way, like here energy is released, clearly some mass is lost in this reaction. So this constituent nucleons have more mass, and the nucleus is having, let us say, lesser mass. Okay, let me call this as small m, 4m, and this is like capital mass m for the nucleus. So this, there is a mass lost, so this 4m is bigger than m. Some mass is lost, and this mass is now converted into energy. So that is the concept here. So with the reference to nuclear binding energy, why the mass of the nucleus is less than the sum of this. So we will say that the mass has to be given up. This is what is the definition of binding energy. It is the surplus energy that should be given up by the constituent nucleons, so that they must come, so that they come, how do you say that, it is the surplus energy that needs to be released if the nucleons want to create a nucleus. Okay, so that much energy will be released, and the expression will be binding energy delta m into c square. That's it. So this is what we will write in this. Now let us go for this reaction now. The polonium 210 decays by alpha emission into lead 206. The following data is available. Calculate in MeV the energy released in this decay. So we want to find the energy released in this decay. So there are two methods here, and I will tell you. So I'm going for the method number one, which is more suitable. Method number one is, first of all, we will find the delta M, and we are not going to change the unit. We can clearly see that the unit for the masses is given in AMU. It is given in atomic mass unit. Let us write the reaction. Polonium 210 is giving you lead 206, and it is resulting in helium 4. This is the reaction that is taking place here. Atomic number is not given anywhere. Yeah, atomic number is not known, so only the mass number is given. Anyways, the mass is given, so the nuclear mass of polonium is given. So method number one is that we will first find the change in mass. So if we say that a lot of energy is produced in this reaction, it means that the polonium was having more mass and lead plus helium is having lesser mass. So this mass will be more, this plus this will be lesser, so this should be more. Yes. So we will find the delta M. So it will be this minus this plus this. So I would be using my calculator now, and let's see. We have to substitute each and every value, like not losing any significant figures here. Minus 205.92945 minus 4.00151. Yes, so this is coming out to be positive 0058 AMU. So this is the mass which is lost. Polonium is having more mass. Lead plus alpha is having lesser mass. Where is that mass going? That mass is converted into energy. Simple. And we are not converting this into kgs. We keep it like that. Now, here is the trick. We know that 1 AMU mass, when converted into energy, produces 131.5 mega electron volt. So this much of the mass will be producing the energy of, you will multiply this value with 0.0058, and the unit will remain the same, that is mega electron volt. Directly you would be getting the answer in MEV. So we are not working with SI system. We are not converting this into kgs. I will tell you about the method number two, but let us first calculate this. So this multiply by 931.5, and I am getting the answer as 5.4027 mega electron volt. So yes, so that can be written as 5.4 mega electron volt. Now, this is the method one. Now, what is happening in method two? I will not be doing it. I'm just going to tell you. Method number two. Method number two is that, first of all, we have this mass. We have to calculate this mass anyways. Then we will convert this into kgs. So 0.0058 AMU. And that will be 1.66 into 10 power negative 27. This will become in kgs. And then we will find the energy in joule, that is mc square, where the value of c will be 3 into 10 to the power 8 meter per second. And then you will get the energy in joule, and then you have to convert it into electron volt and mega electron volt by using the conversion factor. So this is a very long and a method in which there is a very high probability of committing some numerical mistakes or some calculation mistakes. So we would be preferring to use this method. This is the method that you have to do in these kind of questions. This conversion, like 1 AMU is equal to this, you have to remember it. And I believe this is given in the data booklet also, you can verify. So we would be using this, and directly we get the answer, which is 5.4 mega electron volt. I believe everything is clear now. Let us move to the next question. The polonium nucleus was stationary before the decay. Show by reference to the momentum of the particles that the kinetic energy of the alpha particle is much greater than the kinetic energy of the lead nucleus. Okay. Okay. This would be taking time. The mass is given, and we can just assume the mass to be 210. Okay, no problem. Let's see. So let us say that this is the polonium, and the polonium is divided into two parts, like this and this. So this particle is divided, this is 206, and this becomes the 4, because this is basically the alpha and this is basically the lead. Yes. So polonium was initially at rest. So we would be applying completely. We are going to go for the mechanics topic now, the conservation of linear momentum. So this is the case of explosion, and in the case of explosion also, these are known as super elastic collisions. They are also known as super elastic collisions. Why? Because in this energy is created. Earlier, the polonium was not even moving. So what was the kinetic energy of the polonium earlier? Zero. But now, obviously, because kinetic energy is scalar, we would be adding these two kinetic energies. It is not equal to zero. Clearly, energy has been created. So that kind of a system, that kind of a situation, we call it super elastic collision. Although it is not a collision, it is explosion. Anyways, so we will first apply the conservation of linear momentum principle. So the mass of the polonium is 210, but it is the velocity is zero. This is what I am doing. M into U. Initial momentum is m into V1 plus this m into V2. So this is moving with V2, this is going with V1. This is 0 because initially the polonium is not moving. It is 210 into 0. And this mass small m is a 4. And the 4 into V1 plus this mass will be 206, and that is V2. This is 0. From here we can clearly find the momentum or the velocities here. Um, okay. V2 will be taken as negative also. Sorry. Because of the sign convention, V2 is negative and V1 is positive. And this is 0. So 206 V2 is equal to 4 V1. So 206 by 4 is equal to V1 by V2. 4. Okay, let us keep it like that only. So V1 by V2 ratio we have found. And now we want to find the ratio of uh, kinetic energy. Can there be an easy method? We can do the momentum also. So M1, yeah, that will be equal to 1. Then we can apply the p square is equal to 2mk also. Yeah. Okay, so this is method number one. I will tell you the another method also that is far more easier. Now the ratio of the velocity is known, and we will create the ratio of the kinetic energy. So half into mass of alpha into the velocity of alpha, which is v1 square, divided by half into 206 into the velocity 2 of this square. So v1 by v2 is this, and accordingly we can substitute this value here. 4 divided by 206 and this square, so it is 206 square into 4 square. Clearly this square is getting cancelled out, so the ratio is coming out to be 206, and this is the kinetic energy of alpha divided by kinetic energy of lead. Clearly the kinetic energy of alpha is 206 and the kinetic energy of lead is just 4. So it is this ratio. So we can clearly say that yes, the kinetic energy of alpha will be much more than what it is for the lead. And that is definitely because of the mass. But there is an easy method also. So you can just pause the video here. You can take the rest. You can note these things and take the rest for 1 minute. And then we will go for the next method. And I am going for the next method now. So we can just say, instead of substituting these values, we can say that the initial momentum is 0. The final momentum is, like, for the alpha it is p1, and for the lead it is p2, and that is taken as negative. Clearly p1 is equal to p2, and so the ratio of p1 by p2 is 1. Now there is a simple formula that we do in the mechanics. P square is equal to 2mk, and um, momentum is the same in both of the cases. So clearly 2 mass of alpha and the kinetic energy of alpha is equal to 2 mass of lead and the kinetic energy of lead. 2 and 2 gets cancelled out. So kinetic energy of alpha divided by kinetic energy of lead is equal to mass of lead divided by mass of alpha, which directly gives you the answer as 206 by 4. So if you know this formula, the things become quite easy. If you know this formula, like we have done this in the topic of mechanics, and which is very very important formula. So if you do not remember it, now you can remember it. Okay, so this becomes a very small question for you, and very easily you can say that yes, the kinetic energy of the alpha will be much more than that of the lead. Okay, dear students, so this is how we do it. Let us move to the next question. I will show you the mark scheme later, and I will show you all the answers. In the decay of the polonium 210, the alpha emission can be accompanied by the emission of gamma photons, all of the same wavelength, that is this. So there is gamma is also coming out in that nuclear reaction, but all the gamma radiations are monochromatic, they have the same wavelength. Now that is really confusing. Why do they have the same wavelength? Why there is no continuous spectrum? Discuss how this observation provides the evidence for the discrete nuclear energy levels. So why is that? Because when, first of all, let us understand why gamma is emitted. This is polonium. Polonium converts itself into the lead, but this lead, when it is created, it is in the excited state. Even the nucleus is in the excited state. We are not talking about the electrons in the shell, shell number 1, 2, 3. We're not talking about the Bohr's theory here. We're talking about within the nucleus. So within the nucleus, now the lead is going into the ground state. So even here some energy is liberated. This energy which is liberated, the frequency of this is very very high, and it is in the range of gamma. It is in the range of gamma. So this is the energy which is released here. Now this energy is released from the nucleus, it is not released in the atom. It's not about the electronic transitions, it is about the proton transitions. Like it has to be there. So we will say that might be that there is only one shell like this and this, like two shells. So the proton is jumping from one shell to the another shell, and that is why the energy released is having only one and the one particular frequency, and other frequencies are not there because proton is jumping only from one shell to the another. If let us say it was, there was another shell and it was jumping from this also, so there is a possibility of two more frequencies. So there will be three total different type of gamma radiation that will be found in the spectrum. If there was this kind of a case, there will be three different frequencies, but that is not the case. It means that in this particular case there is only two shells, and that is why it is having one particular frequency. And that is why we can say that this is, yes, this is the evidence of the discrete nuclear energy levels, and might be that the proton is also making the transitions. Nothing is clear as of now. We don't know actually whether it is taking place or not. What is happening, we don't know. Our books are not teaching about the energy levels of the proton, but we just know that because this phenomena exists, it gives us an indication, it provides the evidence that there must be nuclear energy levels, but we are still not sure about it. Anyways, let us move next. Okay, a sample contains 5 gram of pure polonium 210. The decay constant of the polonium is given, that is this, and lead is stable. Calculate the mass of the lead 206 present in the sample after 1 year. Okay, dear students, so this question is from the decays, and so we can say that it is from topic 12. Yeah, 12.2 or 12.3. Let us go for the formula now. So the formula that we are going to use is n is equal to n naught e raised to power negative lambda t. From this formula, we can clearly find the number of polonium left. So see, n naught, you can say n naught is the number of initial number. Like we can say it is the initial number of polonium nuclei, and n is the number of polonium nuclei left in the sample. Okay, so this formula is actually valid on the number of the molecules. It can be applied on the mass also, but they want you to comment on the mass of lead, but this formula will be only for the reactant side, that is only for the polonium. So from here you can find the mass of the polonium left, which will be equal to the initial mass of the polonium negative lambda t. So we can first find how much is the mass of the polonium which is left in the sample. We will find that by using our calculator here. So the mass is given as 5 gram. So if the unit is gram here, so you would be getting the answer in the gram. So that is e raised to power negative lambda t. So lambda is 5.8 into 10 to the negative 8, and the time is 1 year, so it is 365 into 24 into 3600. Okay, so there will be an extensive use of calculator here. So I will not be using my calculator showing you the calculation here. So we will see what is the value of the mass that is coming. Okay, so we will find that value of mass. I will see it in the mark scheme now. And okay, let us go for the mark scheme and see what is the value of m that is coming, and then I will explain you these things again. Let us first go for 6c, and then I will show you all the answers. Yeah, so the undecayed mass here, you can clearly see it is coming out to be 0.8 gram. Okay. Uh, yes. So here, yeah, so this is coming out to be 0.8 gram. It means that the mass which has undergone the decay is decayed mass. You started with 5 gram minus 0.8. So it is 4.2 gram of the polonium. So 4.2 gram of the polonium has decayed. Now we will find the number of nuclei of the polonium which have decayed. So that will be equal to the number of moles, we can say. So number of nuclei, polonium nuclei, that will be first of all the number of mole, this into the Avogadro's number. So this is the number of nuclei of the polonium which have decayed. So according to the reaction, polonium is converted into lead and plus alpha. It means one nucleus of polonium, when it breaks down, it is going to produce one nucleus of lead. So these many nuclei of the polonium have been converted into the same number of lead. So how many number of lead molecules are there? These many, the same. So we can say that 4.2 divided by 210 into Avogadro number is equal to the lead number of lead particles, but we are interested in the mass. So let us say the mass here is m. So m divided by 206 is the number of mole, multiply by Avogadro number will be equal to the number of lead nuclei. Now we are comparing them. Na and Na gets cancelled out. So m comes out to be equal to 4.2 multiplied by 206 divided by 210. So this is the answer, and I think you should be clear with this. I know it has been very difficult question. It's highly confusing. Even I am getting so confused in this. But anyways, m is equal to 4.2 into 206 divided by 210. Concept is that first we are applying this formula, then we convert this formula into the mass. We first find the total mass of the polonium which has decayed, then we find the total mass of the polonium which has decayed, and from that we will find the number of nuclei that have decayed, because we know that the number of nuclei of the polonium is equal to number of nuclei of the lead created. It means that the number of nuclei of the lead is equal to number of nuclei of the polonium decayed. Thereby we are equating them and we find the mass of the lead that will be there in the sample. Now, so that is coming out to be this. So the answer will be 4.2 multiplied by 206 divided by 210. Yes, that is 4.12. So this is 4.12 gram. So this is it. This is how we do this question. Now, the point to be taken is try to understand the mass which is decayed is 4.2 grams and it is giving rise to 4.12 gram. Clearly, there is a loss of mass. If you talk about what is the mass, clearly there is a loss of mass here, because you are literally like, why is there a loss of mass? By the way, because alpha is created. Alpha is the rest of mass. Where is the rest of mass going? 4.2 minus 4.12, that is 0.8. Where is that going? Alpha is being created and alpha is taking up that mass. So alpha is taken up that mass. That is why this mass is not equal to this. That is why we have to follow this much of the big process to do this question. Okay, dear students, so this is a very confusing question. Let us move to the next question. If there is any other part, by the way, no, there is not. So this is it for this question, and we'll see you in the next video. Please share the video with all your friends. Thanks for joining the YouTube channel. All the best.